Right, geometric progressions. Just going to summarise what we went through week before the holiday, because we also had a week's break between now and then, is where there's a constant ratio or common ratio called R between each step in a progression. So we've got 1, 2, 4, 8, where between each number has been multiplied by 2. Or we could generalise that as A, the next one as A times R, the next one as A times R squared, A times R cubed, and so on. So that's a geometric progression. And the nth term can be found if we multiply the initial term A by R to the power of n minus 1, where n is the number of turns, a number of terms in the progression. However, as we'll look at in a minute, when we come to these things about money 4 years onwards, we've got to be a bit careful, because we've got to count the year 0 as well. So it's important to know exactly how many terms included and whether the first one counts or not. Okay? So that was what we were doing last time. Okay? And then we went through a problem or two. I'm not going to go through those in too much detail. But we had the value of the lathe, and that's where we come up against this thing about, yes, it's for 4 years, but how many numbers are in the progression? We've got to include the start and £3,000 as well. So it's 1, 2, 3, 4, 5 numbers in the progression, so R becomes 4, the 4 years that you're doing that for. Okay, it's just a matter of how you do things. And I want to point that out carefully, because I think one of your assignment things involves things over a number of years and the cost of stuff. So be careful. So, moving on from that, we need to consider how we find the sum of n terms of a geometric progression. If the first term of GP is A, the common ratio is R, the sum of the terms can be found by adding them all together. Okay? Now, you can simplify that adding together of all the terms, because it's obvious to anyone that if you put each term in the calculator and then press plus in between them, you're going to add them all up. You can play around with that equation and simplify it to that version when R is a number less than 1, the ratio is lower than 1. You can simplify it to that version when R is greater than 1. Okay, now, if you're interested, and I very much doubt whether you are, because you're engineers, and you'd rather just find the formula and use it. If you're interested, there is a full derivation of those two formulas in your bird books. It's on page 129 of the 7th edition. If you want to see how you get from that to those two, then it's in there. Okay? I'm not going to spend time going through that, because I don't feel you need to. You've got the formula. Okay? So, on the next page, there's one to have a go at. Sum of the first 7 terms of half, 1.5, 4.5, 13.5. What is the common ratio R there? What is it? A half. It's gone from a half to 1.5. What have we done? And then we're going from 1.5 to 4.5. Yeah, the differences are 1, 3, and 9. So what are we doing each time? Multiplying by 3. Common ratio R 3 in that one. Okay. So it's therefore it's an R that is greater than 1. We need to use the greater than 1 version of the sum formula. Find that. Right, guys, so all we have to do here is plug the numbers in that formula. That's the version for a progression where r is greater than 1. So we just put the numbers in. A is 0.5. We've got to multiply that by 3 to the power of 7. Take 1 away from it. Put all of that over 3 minus 1. We plug that into the calculator and we get 546 and a half. Yeah? Okay. Next slide has got another example, perhaps where the common r is a little bit more difficult to determine. Right guys, so again there, where it's a little more difficult to see what the common ratio is, we find that by looking at the second term, we know that's A times R, we rearrange that and eventually we can find the ratio. We then just plug it into the formula we've been given and using the version for R is less than 1, plug the numbers in, come up with an answer. Okay? So nothing particularly difficult if I should ask you to do that in the assignment, yeah? Right. One last little bit to do. The sum to infinity of a geometric progression. Where the common ratio R of a GP is less than unity, i.e. the GP is convergent, if we look back at that last one, as we go through the terms, each successive term is getting smaller and smaller and smaller. And if we go on and on and on and on, it's just going to carry on getting smaller. You'd say that that's a geometric progression that is convergent towards 0. Yeah? The first one we looked at, where the common ratio is greater than 1, that geometric progression is just going to carry on getting bigger and bigger and bigger. It's divergent. It's never going to reach 0 in any way. It's going to diverge to infinity. Okay? So here, if we're looking at one that's convergent, the sum of n terms of a progression simplifies as the number of terms tends towards infinity. Where n is tending towards infinity, the sum of n terms simplifies to a over 1 minus r. What you're looking at is, if let's say you're looking at something where you're looking at a piece of machinery you've bought and then it depreciates by a certain amount every year, we all know eventually that'll be worth nothing more than scrap value. It's converged to being worth nothing. Okay, so that's the kind of thing we're talking about. But that's where you're looking at how long could it go before it's worth next to nothing, or the sum to infinity. The best example I could think of. Okay, as the limit and value of the sum of an infinite number of terms. Again, if you want to avail yourself of the derivation of that formula, it's in your Bird maths books on page 129. So page 129 is pretty full of pure mathematics for no real reason at all, other than for the inquisitive. Okay, so find the sum to infinity for that series. What's r in this case? What's a better way of writing 0.3 reoccurring? No, even better than that. That ain't 0.3, is it? What are we doing to get from 3 to 1? Divide by 3, or multiplying by a third. So r third. Yeah. Guys, so there's that one. Just plug the numbers in the formula. We need A, the first number in the series, which is 3. Divide that by 1 minus r, so it's 1 minus the third. Plug those numbers in your calculator. I really do recommend that you use the fraction button to do these and do it all in one go. And we come out with an answer of 4.5 for that. The sum to infinity for that progression, 4.5. On the next page, there's an example of a more practical nature. A hire tool firm finds that their net return from hiring tools is decreasing by 10% per annum. If their net gain on a certain tool this year is £400, find the possible total of all future profits for this tool, assuming the tool lasts forever. Okay, so it's decreasing by 10% a year. This year they earned £400 from it. So what have we got to find out how much in total they will make off those tools if they go on forever? What are we talking about when we talk about forever? Infinity. So we're looking for the sum to infinity of using the data there. So picking it out from there, what is A? £400. What is R? Is it 0.1 or is it 0.9? Yeah, it's losing 10%. So we've got 90% left every year. Yeah. So then we just plug that into the sum to infinity formula and get an answer. That's probably for 3,900 stuff on a bit, I reckon. That is 4,000. What's I have? I always like to have prepared answers. If I ain't got prepared answers, that's a disaster. Usually ends up. So what we got, guys? 4,000. I reckon you're right. Yeah, 4,000. The trouble is, in the year dot, they'll be getting pence out of hiring the same tools as they are now. You're just talking about the fact that that's got to have a limit somewhere, because it's gradually getting smaller and smaller and smaller. The end of that bit. Okay. Assignment 1. To go with assignment 6. I mean, I did toy with the idea of joining the two together anyway, but those two together are not much more than one assignment, and they still leave a little bit of learning outcome 1, still learning outcome 2 still to be covered. But what it is assignment number 1, using arithmetic and geometric progressions to solve engineering problems. Being issued today, okay, and submitted no later than Wednesday the 16th. Okay, so that's 2 weeks from today, right? And I'll give you a bit more detail on that once we've been through it. Be able to, it's all part of learning outcome 2, being able to apply algebraic techniques, and the criteria being assessed here P2 and P3. P2, solve a practical engineering problem involving an arithmetic progression. So we've done that last time we were here. I'm avoiding the temptation of saying last week. I had a degree student here this afternoon that wasn't here the week before holiday but came in last week because he didn't know it was a holiday last week. And then P3, solve a practical engineering problem involving a geometric progression. Okay, so that's what you've got to do. I've only passed criteria, so we should be getting these away quite quickly. Background. Drilling company need to employ a team of drilling engineers for 30 weeks. They have to keep to a budget of 96 grand for each worker. It's decided to pay the drilling crew, well, it's in a pretty dangerous area, you see, you get paid a lot of money then. Alright. Decided to pay the drilling crew a fixed amount to start the job and then a bonus that increases the wage at a fixed rate for every week thereafter. Be given the job of costing it out. Okay? And talking about and presenting the options of what might be attractive. So, A. Use arithmetic projection methods to investigate a full range of possibilities. You should consider the effect of not having a bonus at all and just paying the same weekly amount versus the effect of having a minimal starting package and a high bonus. Then consider three options within the range, so look at what the range is between no bonus and maximum bonus, right? And decide on three options to look at, and then prepare a short report for your line manager outlining the options and making recommendations in light of the calculations. You want to be thinking about it in terms of which is attractive to the employer in terms of getting people to want to do the job and maybe being able to pay out the least money or whatever, and what is most attractive to the employee. Okay? And then the answer is probably a balance between the two, usually. Right? The second task, drilling machines purchased by your company for 18 grand. Plan to use the machine for 6 years before selling it and purchasing a new one. Expected it will depreciate in value at a rate of 8.5% per year for the next 6 years. So we're talking geometric progressions here. For 6 years, 7 numbers in the progression. Yep, all right. Inflation is predicted to run at a rate of 2.5% for the next 5 years. So you're going to have two progressions here. One is how much the machine's going to depreciate. The other one is how much money put aside today is going to appreciate to partly meet the cost of that machine. Because you're going to sell it at the end, and then you're going to add to that money that's appreciated. What we want to know is how much you need to put in the bank now, so that if it's getting a 2.5% interest for the next 6 years, please change that. Typo, okay, because I changed some numbers from last year's assignment. 96 grand. Where? 96. Keeping the overall wage to 96,000. Sorry. Oh. Steve's looked at this as well. I need him to pick it up. All right. So what you're being asked here is to use geometric progression to work out how much you should put in the bank now so that you've got enough money to make up the difference between what you sell the machine for and what the cost of a new one is. Right? Yeah. Your 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 price of your, sorry, that's the price of the new one that's going to go up by 2.2% a year. Yeah, so you're going to set aside a cash deposit now. Ignore an interest on that cash deposit. You've not been given that. Yeah. Okay. So you're ignoring interest on the cash deposit. Just looking at setting aside money now to make up the difference in the depreciated value and the cost of a new one. So there's two geometric progressions in there, one divergent, one convergent. All right? So that is all you've got to do. Generally on both assignments, gents, please lay out your work nice and neatly. I would prefer it to be typed, if I'm honest, but you might not want to do that. But I have to be able to read it, don't I? Right? Make sure one particular thing to be careful with is to make your decimal points very, very, very visible. Some people just do a tiny little dot and they got scribblings all over the place. Take some pride in your work, make it neat, and show me you're working. So if you've gone wrong, I can see where you've gone wrong, and we can point you much easier in the right direction. Yep. And I like the idea of you put the formula down, then put the numbers in it, do the calculation, okay? And show me any rearrangement of formulae as well if you need to do that. Right. Now, in terms of